So the probabilistic softmax formulation for attention serves three different purposes. First, it makes attention differentiable, which is needed, of course, for us to be able to use backpropagation. Even though attention itself has no learned weights, so these CI vectors, they're not going to be learned, right? The gradients still flow back through attention, so we still need to take the derivative with respect to the different components of the vector Ci. So that's why it's important to have continuous functions like probabilities. Second, the probabilistic formulation allows the model to capture certain types of long-distance context that may have not been captured by the source RNN, because attention considers the entire source sequence at once and learn to keep what's important and ignore the rest. Third, probabilistic attention allows the network to represent uncertainty. Okay, so if the network doesn't know exactly what source word to translate next, it can distribute the attention probabilities over different words and then actually choose the word using the target RNN. So unlike most components of neural networks, attention probabilities are actually meaningful for us as human. Okay, so often when you look at the weights of a neural network, you don't really understand what's going on. But when you look at attention, you can actually tell what they mean. For example, in the case of machine translation, or a question answering system, the attention can actually determine when the question ends and when it starts generating the answer. Now, during training, sequence-to-sequence models again attempts to maximize the probability of each word in the target training sentence, conditioned on the source and all the previous target words. Now, once training is complete and we are given a source sentence that we're trying to translate, our goal is to generate the target sentence. Now, we can generate the target sentence one word at a time and then feed back the word we generated at the next time step. And this is what we call decoding, essentially, right? Because each word from the target network that we generate will be fed into the next layer of the target network to get the following word and so on. So as we discussed earlier, the easiest way to decode is just to select the word with the highest probability at each time step, and then feed this word as the input to the next time step. So that's called greedy decoding, because after each target word is generated, the system has fully committed that this is the correct word, and then it's going to build on that and generate the next word. Now the problem is that our goal from decoding is to maximize the probability of the entire target sentence generated, not to maximize the probability of each individual word. Okay, so it is possible that greedy decoding will not achieve the maximum sentence probability, target sentence probability. Okay, so the book has an example where it says if you're trying to translate the front door is red from English to Spanish, it is possible that the RNN correctly generates the first word for the And then next, the greedy decoder might propose entrance or entrada for front, because in English it says the front door, so it might say la fronta, la entrada, where entrada is Spanish for front, but this is an error in Spanish because in Spanish the adjective should come after the noun. So greedy decoding is fast because it only considers one choice at each time step, and this can be done quickly, but of course it has no way of telling that it made a mistake, and then it can keep on generating even though it made a mistake at a given word. Now, one way to improve the attention mechanism so that it always attends the right word and guesses correctly every time. But for many sentences, this is not possible to guess all the correct words at all time steps until at least you've read the entire target sentence. So what we need to do essentially is to keep a set of candidate sentences at each time step, and then once we're done translating, we pick the candidate with the highest overall probability. And this is similar to beam search, essentially, right? Because in machine translation, decoding beam search essentially keeps the top K hypotheses. So you can say at each word, I'm going to keep the top 3 probable next words, not just the top next word. I'm going to keep the top 3, for example. And then extending each by one word using the top K choices, in top 3 in that case. So you build an entire tree of sentences that are all candidates for the correct translation for the source sentence. So if you decide to keep the top 3, so you're going to end up with 9 sentences after the next word and so on. As you can see, it grows very quickly. Once you generated all the hypotheses, all the candidate sentences, then you can pick the one with the highest probability or the highest score. Okay, so we can look at the visualization of this process. So here at time step 1, I'm starting. So I'm translating that sentence, which is the front door is red. So we have 2 options at time step 1. From the target network, we can either pick la or una. So la has a score of negative 0.3 and una has a score of negative 2.1. Now I'm going to consider both branches and then look at the next time step. Well, I have 2 options here. Here I'm using k equal 2, obviously. So I could use entrada, which has a score of negative 0.8, or puerta, which is door, which has a score of negative 0.9. So at this point, I have 4 hypotheses to test. You can see that from the end there. So 2 in beam 1 and 2 in beam 2. And then in time step 3, at this point, I have more hypotheses to add here. So after each one of them, I start adding the next hypotheses and so on. Now at the end of time step 3, the highest scoring hypothesis in that case will be la entrada can only generate low probability continuation, so this one falls off and we end up with la puerta de entrada, okay, which is the correct translation. Okay, so as deep learning models become more accurate, we can usually afford to use a smaller beam size. We don't have to go big with K. Okay, the current state-of-the-art machine translation model use a beam size between 4 and 8. Okay, older generation models used beam size in the order of 100 or more. So you had to really keep with you a large set of candidate hypotheses. Okay, so this concludes our lecture for this week, and I'll see you in class, and let me know if you have any questions.